Hello everyone, I am Anqi Li. I am currently a PhD student at the University of Washington. It is my pleasure to talk about some of the work that I did with my colleagues on safe and efficient robot learning here at the RSS workshop on geometry and topology in robotics. Recently, we have seen robots venturing from traditional lab settings into a more challenging environment and starting to tackle more diverse tasks. For example, there are robots recently being deployed into terrains that we don't even know much about. We can also imagine that in the near future, household robots being tasked with manipulating a variety of different tools and objects. Traditionally, modeling and control techniques have been used to solve robotics problems. They usually require us to derive a first principle model and then come up with a controller that has desirable theoretical properties. However, as the environment becomes less structured, it becomes increasingly hard to find an accurate model as well as designing a good controller. Data-driven methods, on the other hand, seem to be a powerful alternative in this setting, as they usually make weak modeling assumptions. Moreover, they can also improve their performance as they collect more data. However, it is still unrealistic to directly apply these data-driven methods into robotics problems due to a number of concerns. For example, it is hard to have any safety guarantees during learning and after learning. It requires a lot of data, the learned policy is hard to be interpreted, and the learned policy can often exploit the environment, such as the reward function. Here on the right, there is a robot whose original goal was learning to walk. However, it exploits the dynamics and the reward function and ends up generating this very weird behavior. In most of the previous work on learning robot policies, people often use fully connected neural networks to parameterize the mapping from state to action, namely the policy. On one hand, these fully connected neural networks are powerful because they are universal function approximators. However, this also means that they're extremely inefficient, both in terms of samples, parameters, etc. In fact, the current success in deep learning highly relies on finding the right neural network architecture, which can exploit the structure of whatever problems we're trying to solve. For example, we choose convolutional neural network to leverage the spatial structure of images. We know that nearby pixels are more related than far away ones, and the positions of the objects are less important. Therefore, in order to make robot learning practical, an important or an essential step we need to take is to find a policy class which can encode structure in robotics problems. But even before that, we need to first figure out what kind of structure do robotics problems really have. In this talk, I will first talk about the geometric structure commonly exists in robotics problems. A large part of it is introduced by the kinematics of the robot. Next, we will look into more complicated robotics problems, which involves multiple objectives. And finally, we will see how we can leverage such structure to enable safe and efficient robot learning. Let's now focus on the first part, which answers the question of what kind of structure exists in robotics problems. To start with, let's consider this example where we want this robot manipulator to reach our target. We know that we can move this robot by changing its joint angles. Here in this example, this Franka robot manipulator has 7 joints. These 7 joints uniquely determine the configuration of the robot. Therefore, we call this 7 degrees of freedom joint angle vector the configuration space coordinates. However, it is oftentimes not at all intuitive to consider robot motions in the configuration space. In many cases, it's often easier to consider the motion of points on the robot body. For example, the end-effector's position relative to the object is the most relevant to the target reaching task. As another example, for obstacle avoidance, what's perhaps more relevant is the distance between the points along the robot body and the obstacle. The kinematics of the robot is a function that translates what is going on in the configuration space, where we can actually move the robot, into what is going on in the space which we really care about, which in this case is the end-effector position. Now let's take a deeper look into the kinematics function of the robot, as it fundamentally determines the geometric structure of the robotics problem. The input of the robot kinematics is the joint angles and a base pose, which is the position and orientation of the robot base. Our goal of the robot kinematics is to compute the end-effector position, and based on this base position and the angle of joint 1, we are able to compute the pose of link 1 or any points on this link 1 of the robot. And then with that and joint 2 angle, we can compute similarly the pose of link 2 and so on and so forth, and we can do that all the way to the end effector. If you're a deep learning person, it may be easier to think about this robot kinematics as a chain of layers. Each layer corresponds to a rigid body transformation, which is like this. And this rigid body transformation is determined by, for example, the length of the link and where the joints are located. And in fact, we can just implement all of these in automatic differentiation libraries like TensorFlow or PyTorch. So abstractly speaking, we can consider this forward kinematics as nothing but a module, and that potentially lives in automatic differentiation libraries. As we saw on the previous slide, this module contains a chain of rigid body transformation layers. Because we care about the motion of the robot rather than just a static configuration, it is important to understand how to translate joint velocity and acceleration into an effector space. For velocity, this is given by differentiating through the kinematics. This operation in geometric terminology is called push forward. We can further compute the end effector acceleration by taking second-order time derivatives. If we actually implement this forward kinematics module in Auto-diff libraries, we notice that these automatic differentiation tools provide us with very powerful APIs for dealing with the geometric structure of the robotics problems. For example, if we want to compute the end effector velocity, we need to implement originally this push-forward operator, and the closed-form solution for this push-forward operator can be quite hairy because the kinematics itself is pretty complicated. However, if we implement the forward kinematics within the Auto-diff libraries, this push-forward operator can be now efficiently implemented by just a single call to the Jacobian Vector Product API, or JVP, that is naturally and natively supported by Auto-diff libraries. We can do similar things for an effector acceleration. In this case, we need to make a couple of more calls to the JVP function. So to summarize this part of the talk, we see that robot kinematics provide the geometric structure of many robotics problems. And we can think of the forward kinematics of the robot as a module that consists of a chain of rigid body transformation layers. By using Auto-diff APIs, we can easily translate the motion of the robot in the configuration space into the test spaces. With that, let's now look into how we can make use of the geometric structure in complicated multi-objective robotic tasks. Let's consider the same Franka robot that we saw in the previous example, but now we not only want the robot to reach the target, but we also needed to avoid collision with obstacles in the environment, and furthermore, we may want the joint angles to stay within the joint limits. For these types of multi-objective tasks, we could potentially generate policies from scratch. For example, we can use different types of planning methods, such as searching or trajectory optimization. We can also use reinforcement learning to learn a good policy. This, to me, looks a lot like trying to make a sculpture out from clay. You can end up with an extremely delicate, potentially optimal policy. However, the entire process requires a lot of time and a lot of computation. Moreover, if we are handed with a different task, we probably need to go back to the clay and start from the very beginning. And as the saying goes, don't let perfect be the enemy of good. This motivates us to look at something very different. The policies that we're going to look at for the rest of this talk is something more like Lego blocks. Of course, there's only a certain level of resolution that you can get to with these Lego policies, meaning that we will likely get something that's suboptimal. However, each of the single Lego blocks is simple and composable. Once you're handed with a new task, you can quickly find a few pieces from your library and come up with something reasonable. This means that these policies are reusable. Moreover, since you can find and assemble these policies so quickly, you can also have a reactive policy. So the key questions for those Lego policies are, first, what does a policy Lego piece look like? And second, how can we put these Lego policies together? This requires us to take a look at a framework called Riemannian motion policies, or RMPs. Going back to this example of target reaching in cluttered space, we can decompose this problem into a few simpler ones, which gives us the notion of subtasks. One subtask, for example, could be just target reaching without worrying about the obstacles, which is the same as the one that we saw earlier. We can have another one that only considers avoiding obstacles. We could have another one that deals with joint limits. Recall that in the first part of this talk, we have this forward kinematics module that allows us to compute the task coordinate, which in the previous example was the end effector position. Now, since we have multiple subtasks, each of them can have their own subtask space. For example, the end effector position is more important for target reaching, but the distance between many points on the robot and the obstacle are perhaps very relevant for collision avoidance. Therefore, we now have a forward kinematics module that outputs not just one, but many subtask coordinates. It could be end effector position, it could be distance between the robot and an obstacle. It could also just be the joint angles, since it is useful for handling joint limits. With that, we can finally talk about what does these subtask policies for Lego pieces look like. We describe each subtask policy as a Riemannian motion policy that lives in its own subtask space. Each RMP consists of two parts. First, there is a desired acceleration policy. For target reaching, we can imagine this Lego policy pushes the end effector toward the target. For collision avoidance, we can have each Lego policy pushes a part of the robot away from the obstacle. The second part of an RMP is an importance weight policy, which is a matrix-valued function characterizes the trade-off between subtasks. For example, when the robot is close to an obstacle and is moving towards the obstacle, the importance weight of the collision avoidance policy should be high enough, while the weight should be close to zero when the obstacle is far away from the robot and the robot is moving away from it. Therefore, we now know that each Lego piece policy is an RMP that lives on its subtask space. We can now look into how we can put this Lego pieces policy together to get an actual joint configuration space policy that we can actually execute. As we talked about earlier, we have Lego piece policies living under their corresponding spaces. For example, we have a target reaching policy acting on the end effector space of the robot. We can put collision avoidance policies along the body of the robot. Finally, for each joint, we can have a joint limit policy. With these, we can use an algorithm called RMPflow to put these Lego pieces policy on different spaces together, and gives us a joint space acceleration policy, which can be actually executed on the robot. What this RMPflow algorithm is doing is essentially solving this weighted least square optimization problem. Here, in the terms in the green box, is effectively the acceleration in the K subtask space if we apply joint acceleration Q double dot, which is something we saw earlier in the first part of the talk. Therefore, within this norm is the deviation between the effective acceleration in the K subtask space and the desired one, which is AK. And since each subtask has different importance weight given by mk, we measure the deviation with the norm induced by it. What this optimization problem effectively means is that we want to find a joint acceleration policy such that when projected onto each subtask spaces, it matches the desired acceleration for that subtask well. Furthermore, we observe that this optimization problem has a closed-form solution, which is given right here. It turns out that we can also compute this closed-form solution efficiently using automatic-differentiation libraries. If you're familiar with differential geometry, this configuration space M and F are closely related to the pullback operator in differential geometry. This means that we can consider this RMP squared module, or we can consider this RMPflow algorithm overall as a module living in Auto-diff libraries. It contains the forward kinematics submodule and also each of the subtask RMP submodules. We show that the combined policy by this RMP squared module with the RMPflow algorithm is stable as long as each subtask policy satisfies certain control Lyapunov condition. This stability can also provide safety guarantees to the system with properly designed, for example, collision avoidance RMPs. As a quick summary, we use RMPs as Lego pieces for policies, and we use this RMP squared module implemented in Auto-diff libraries to put them together into a policy that we need. This RMP framework has been applied to a wide range of robotic systems. This is a demo from the original RMPflow paper, where the RMPflow policy is used to control a dual-arm manipulator to open a drawer and put an object inside. In one of our papers, we also managed to use this RMPflow policy to control a multi-robot system, where the two teams are tasked with moving and maintaining their corresponding formations while avoiding collisions with other robots. As quick summary for this part of the talk, we can tackle multi-objective robotic tasks using modular composable policies. Furthermore, we can use this RMP squared module implemented using Auto-diff APIs to combine these composable policies together into a configurations policy, and we can combine them in a geometrically consistent manner. With that, we can finally switch gear and look into how we can leverage this RMP squared policy class to enable safe and efficient robot learning. In existing work on robot learning, fully connected neural networks are often used to parameterize the policy. As we talked about at the very beginning, fully connected networks are fundamentally inefficient. So what we decide to do here is to use this RMP squared module instead to represent the policy, because this RMP squared module naturally encodes the geometric structure of the robotics problems and can provide nice theoretical guarantees. To enable learning, we need to think about what can be learned or parameterized within an RMP squared module. First, we can parameterize these Lego policies, namely subtask policies, which involves parameterizing an acceleration policy and the importance weight policy. Perhaps less obviously, remember that each Lego piece lives in its own subtask space. This means that we can also parameterize the forward kinematics module so that we can find a more efficient task coordinate. Let's first look at parameterizing RMPs. In order to represent the positive definite importance weight matrix, what one can do is to predict first the Cholesky decomposition, and then the importance weight matrix can be obtained by multiplying this Cholesky decomposition matrix and its transpose. One neural network architecture to achieve this is here shown on the right. To represent the acceleration policy, we can choose to either directly use a neural network or parameterize a potential function first and use the acceleration derived from it. For example, in one of our work, we decided to simply put attracting potentials along a demonstration trajectory, which is shown here in this figure. As we just talked about, another possible way of parameterizing RMP squared module is to use learnable transform maps or forward kinematics. Inspired by a generative model called normalizing flow, what we choose to do is to learn a diffeomorphism so that the original complex motions become straight line motions in this latent subtask space. In order to do this, we consider this mapping as a composition of a sequence of simple diffeomorphisms, and within each simple diffeomorphism, we scale and translate a subset of the dimensions, which is shown here as CBs. And the scaling and translation functions are each parameterized by a neural network. We test this task map learning technique on the Lanza handwriting dataset, which is a standard 2D learning from demonstration dataset. And here, the white dotted lines are the demonstrations, and the red lines are reproductions, which is basically straight line motions in this learned subtask space. I additionally show the vector field to give you a sense of how this motion generalized. We see that our learned diffeomorphisms are able to warp straight line motions into very complex shapes. Now we know all these different things that could be parameterized within an RMP flow policy. Let's take a step back here. I think what is even more powerful about RMP flow policy or RMP squared module is that it allows us to not learn certain things if we already have information about them. For example, we can reuse subtask RMPs across different tasks, although we could potentially parameterize out task maps within the forward kinematics module. The kinematics itself may already be sufficient for many subtasks. We can hand design safety-critical RMPs, such as collision avoidance and joint limit RMPs, such that the robot never hits any obstacles or its joint limits. Finally, if we're given expert demonstrations, we can encode it through imitation learning, or we can also warm start learning if we have a reasonable policy to start with. Now let's look at how RMP flow policy can actually enable safe and efficient learning through the lenses of two case studies. In the first one, we consider learning RMP squared policies from human demonstrations. In this example, we have a human, who's our collaborator Asif, teaching the robot how to go around the cabinet door to reach the handle of this cabinet door. And during the skill reproduction, we altered the configuration of the cabinet door. As you can see, some of them are open and some of them are pretty much closed. And we can see that this robot can still be able to generalize and achieve the task. To demonstrate this feature even further, we can even move the cabinet door in the middle of the execution. And we can see that the robot can immediately adapt to this change and achieve the task. Here's another example where we have a human, who's again our collaborator Asif, teaching the robot to close the drawer. Then during the reproduction, we start the robot with very different initial configurations, as you can see, and we see that the robot is able to achieve the task from all of the initial configuration, although for the upper two cases, the robot takes a little longer to achieve the task because the initialization is far away from any demonstrations. Another feature of this RMP squared module is that we can use the learned subtask policy and combine it with other hand design policy during test time. Here, this is still from the drawer closing task, but now in simulation, and we have also added an additional obstacle on the way of the robot. And we see that the robot can just automatically adapt to it without any further learning. Next, we will look into how reinforcement learning can benefit from this RMP squared policy. And reinforcement learning has recently shown great success especially in games. However, there's still great difficulties in directly apply them into robotics due to concerns on, for example, safety and sample efficiency. We hope that learning with the structured RMP flow policy can mitigate some of the limitations of RL. Here we consider a task where we want a Franka robot to reach the grain target without colliding into any of the gray obstacles. For this reinforcement learning problem, The state consists of joint angles, joint velocities, target position, obstacle positions, and obstacle radii. The action is the joint acceleration. We train two types of policies for this task. The first one is a direct, fully connected neural network mapping from state to action. I will refer to this policy as NN for the next couple of slides. The other is an RMPflow policy, which consists of a learnable target-reaching RMP and hand-designed collision avoidance RMPs and joint limit RMPs. We trained both policies with 500 iterations of proximal policy optimization, or PPO, which is a standard reinforcement learning algorithm. As you can see that after all this training, the neural network policy is still far away from being reasonable and still results in collision with obstacles in the environment, while the RMPflow policy managed to achieve the task. If we look at the quantitative results, we can see that the RMPflow policy achieves good performance pretty quickly, while the NN policy just struggles to improve. Moreover, here's the plot for the percentage of safe episodes at each stage of learning. When trained with RMPflow policy, we see that the robot never collides into any obstacles throughout learning, meaning that the RMPflow policy is always safe. So, as a summary of this talk, we have seen that geometric structure commonly exists in robotics problems. Although the math behind it is quite technical, we can make use of modern Auto-diff libraries to easily handle such geometric structure. We also see that by using such structure, we can make robot learning safe, efficient, and explainable. With that, I will conclude my presentation. Thank you all for listening. I would also like to thank all my collaborators for their input. I have put my email here, so feel free to send me an email if you have any questions or want a copy of my slides. Finally, it is my pleasure to introduce our next speaker, Professor Michael Brownstein from Imperial College London. Professor Brownstein has done a lot of amazing work on geometric methods for machine learning and data science. He'll be talking about geometric deep learning.